Welcome. We wish now to discuss a solution of a transcendental equation. In particular, the transcendental one that we're looking at is tangent of x minus x is equal to 0. And to do this, we will use an approach called Newton's method, which we will talk about in today's video. First, some definition. So when we're talking about a transcendental, we are speaking in terms of the equation of one that involves a function which cannot be constructed algebraically by a finite number of simple polynomials. In our present context, as we just mentioned, we're looking at the trigonometric tangent function, and I'll say a little bit more about that here in just a second. But I do want to make a side note before we go on with the video here. And the side note is to look at the word transcendental, or something that transcends. Okay, transcend literally means rising above and going beyond. And the side note that I wanted to mention here is that of God, because God really does transcend humanity. He rises above and is beyond what we are as human beings. And as a matter of fact, in Isaiah chapter 55 verse 8, he makes this beautifully clear by saying, "For my thoughts are not your thoughts, neither are your ways my ways, declares the Lord." Now, speaking about a transcendental equation as we're talking about in this case, let's remember some things that were not transcendental in nature. So previously we had talked about, for example, in the two train problem, so this is an earlier video that we talked about. We had an equation that resulted in the following form. And from here, we were able to show that we got something of the form like this. We can call this our polynomial, okay? So, for example, I could say this is some polynomial p of x is equal to 0. In our Giancoli video, where we were looking at his problem 2-44, we had another non-transcendental equation that came out to be the following: t tilde squared minus 11.1 t tilde minus 11.1 is 0. And here we can just call all of this our polynomial. Let's say it's a polynomial p tilde as a function of t tilde is equal to 0. So both of these, whether it's the p or the p tilde, both of these are not transcendental in nature. However, now we're interested in something that is transcendental. And, well, why is it transcendental? A reason why this tan x minus x equals to 0, which I could just call this my f of x polynomial. Let's suppose I just call this f of x is equal to 0. Well, it involves the tangent, right? And you may recall that the tangent function can be written in terms of an infinite power series that looks like this. Okay, so you'll see right away that we're taking a summation beginning at n equals to 1 and going all the way to infinity of this expression, which, if you were to write it out term by term, is going to have the following form. It's going to be x plus x cubed over 3 plus 2 times x to the 5th over 15 plus, and the dot 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 means that it goes on ad infinitum, so forever. In this expression here, you'll notice that we have a term b with a subscript 2n. The b sub 2n term there are the even-numbered Bernoulli numbers. So if you take a look at the Wikipedia site that I've listed here, they mention the first 4 even-numbered Bernoulli numbers. B sub 2 is 1/6, and B sub 4 is minus 1/30th, and B sub 6 is 1 over 42, and the fourth Bernoulli number, even number, B sub 8 is again minus 1 over 30, and etc., etc. And if you're interested in knowing more about those, you can visit the Wikipedia site and see what that is. But let me just say one quick word about this, that in fact this first term here in the infinite sum is when n, of course, is equal to 1, because we're doing a summation. Okay? So in the first sum, in the first case, when our index n is 1, that means that, let's just take a real quick look at what that means so that we're straight about this. So we have b, so when n is 1, we have b sub 2n is going to be b sub 2 times 1, which is b sub 2, okay? And so now you have these other terms here. You have b sub 2 times minus 4 raised to the 1 power times 1 minus 4 raised to the 1 power. I'm just following the form here. Divided by 2 times 1 factorial times x raised to the 2, n is 1 again, so it's 2 times 1 minus 1. Let's look at what all of this means. This means that we have b sub 2 times minus 4 to the 1 power is minus 4. 1 minus 4 to the 1 power, 4 to the 1 power is just 4, so 1 minus 4 is minus 3. 2 times 1 is 2. 2 factorial is 2 times 1 by definition. This is times x raised to the 2 minus 1 is x to the first power, or just x. So really, look at what we're getting here. We're getting b sub 2 times minus 4 times minus 3 is a positive 12. 2 times 1 is a 2x. So this is b sub 2 times 6x. But b sub 2 is the Bernoulli number 1/6 from here. And so putting 1/6 in for that, that means that we get 1/6 of times 6x, or all of this reduces to just x, which happens to be the first term in that infinite sum. Okay, with that, with a better understanding of how this equation, or this form that we're trying to solve is transcendental because of this infinite sum, now let's move on to the next page, and let's remind ourselves, first of all, what tangent of x, what the graph of that looks like. So if we were to come down here, I have taken an image from the following website that I cite here, which gives us the graph of tangent of x. So this is a graph of tangent of x. Now, tangent of x is a periodic function with a period of pi. Okay? Now, what does that mean? That means that if you were to just look at these segments here, from here to here, in between here we have a pi segment here, and notice what the graph is doing. The graph is coming along this way, but then if we go over 1 pi, this is also a interval of pi, the graph repeats itself, and it continues to repeat itself ad infinitum. Okay? So that's why we say that it's a periodic function of a period of pi radians. Now, what we have in this figure here, drawn with the red curves, is the function tangent of x. But in our equation that we're trying to solve for x, this tangent of x minus x, let's now graph the value of x. So the graph of x is going to be a line. So this is the graph of a straight line of slope at 45 degrees. That is to say that when I go over pi over 2 radians on the x-axis, I'm rising up pi over 2 radians up on the y-axis. Now over here, you'll notice that we have a 5. As you probably know, pi has a value of approximately 3.14. Okay? So let me say approximately. So that means that 3 pi over 2 has a value of approximately, if you were to multiply pi times 1.5, that is what 3 halves is, you're going to find a value of approximately 4.71. So 5 is going to sit just to the right of this somewhere. And so if I were to extend this line up here and intersect it with the 5 over here, this is where I'm saying 5 ought to be. While this doesn't look the way we would have expected because it's not drawn in a particular square scale, you'll notice that our graph, this graph of the function x, is going to go at x is equal to 0, it's 0. So it's going to have 1 point at the origin and the second point at the value at the ordered pair 5, 5. And so if I were to connect these dots, I'm going to have a graph that looks like this. Now what we're interested in is where these two graphs actually intersect. So if I were to draw the intersection point between the graph of, this is the graph of x, and the red one, as we said, is the graph of tan x, where they intersect, the first solution is going to occur right over there. You'll notice that this point of intersection is just a little bit to the left of the 4.71, so it's a little less than 5. You'll also notice that out here, we're expecting another solution way out over here. And in fact, if you were to extend the graph of x and the graph of tangent of x, you should have an infinity of these intersections. So you should really have the solution set to our transcendental is in fact infinite. We're only going to look at the very first value, which is this value over here, which, as we just noted a moment ago, is at some value a little bit less than 5. So I have now on the next page shown that we're over here, which is a little bit less than 5. And so to get at a solution on this, let's now take a look and see what is Newton's method. So Newton's method says the following. Let's go to the next page. Here it is. It says that, in fact, it's an iterative approach. So Newton's method is an iterative approach. Where you'll notice that we have an x, what I'm calling an x sub old value that we're going to begin by guessing. Once we make a guess on our x value, then we go through the machinery of Newton's method, which is in the box here. And after going through that, we're going to get an updated value for our x. That updated value then becomes, in the next iteration, x old, and we go through the machinery again for the second time, and we wind up with a third value of x. And then we go through another iteration where that value then becomes the x old, and this continues and continues until as such time that the difference between your old and your new x values, the absolute value of that difference, is quite small or even 0, as we will illustrate. So let's first of all look and see what we're talking about here. This is our equation. Tangent of x minus x is equal to 0. And as we noted earlier on in the video, we're going to set our function value, f sub x sub old. Again, the variable that we're interested in here is what we're calling x sub old, is equal to this equation right over here, with, of course, x sub old substituted in the place of x. Okay? So really, we're looking at now this as our f sub x value. Our x sub old value is going to be guessed by looking at this point right over here. So, like I said, we're going to begin with a guess, okay? So let's just guess that x sub old is about 4.5 for our first iteration, for iteration 1. Okay, so we'll guess that x sub old is about 4.5 because 5 is sitting a little bit to the right of that, as we mentioned earlier. Now coming back to this function, if f of x is equal to tan of x minus x, that means that if we differentiate both sides, we're going to get f prime of x sub old the derivative of tangent of x is secant squared of x, so we're going to get secant squared x sub old. The derivative of x, or minus x in this case, is just minus 1. Okay, so here we have, in these boxes, we have the function value f of x old, and we have its derivative f prime of x old, and those are the things that we needed to solve Newton's method up here. Okay, so let's go ahead and try this out for size. Here we have set up a table. This I, I'm letting I stand for iteration. And as we said, let's just start with a guess of 4.5, and I'll use 5 decimal places here just to be consistent. Okay, so we're taking our guess value as our first iteration's x value, x old, and now we plug in 4.5 into our function value. Our function value says tangent of x old minus x old. So you'll need to have your calculator to do that, and there's one word of caution. You'll want to have set your calculator to radian mode. The reason for that is because this value that we're talking about is in fact in radians, okay? Let me write this over here. So x sub old is in radians. If you do that in your calculators, go ahead and stick in 4.5 in here, and then take the argument is 4.5, so take tangent of that and then subtract 4.5 from that. You're going to get a value 0.13733. And f prime of x old is up here, so let me not take time to rewrite that. It's right over here. And then if you stick in 4.5 again in radian modes in your calculator, now secant, you'll probably remember that secant is the inverse of the tangent. So if you were to do the tangent of 4.5, again being in radians, then take the inverse of that and then square that result, you're going to get secant squared of x old, and then subtract 1 from that, and if you do that, you should find that the value is 21.50485 out to 5 decimal places. Now we put everything into Newton's formula. So the Newton method said that x new is x old minus f of x old divided by f prime of x old. Okay, so by doing that, you should now be able to find an x new value, and it comes out to being 4.49361. And now take the difference of this value and the first value that we started with, and if you subtract that and do it in absolute terms, the difference is already, you'll see that it's kind of small. And the reason for that is because we started out with a pretty decent guess. We could see from the graph where our first root should be, and we were pretty close in our guess because it's 0.0 1 for all intents and purposes. Now, I went ahead and left the values for iteration 2, and you can verify that on your own. Let's look at the last iteration. And by the way, in the second iteration, note how small the difference between the x old and x new values are. It's 0.0002. So it's almost zero for what most engineering work would need. It's, for all intents and purposes, good enough. But let's go ahead and do one more iteration out to 5 decimal places. So now the x new value becomes our x old value in our third iteration. So this is 4.49341. And if you plug this into your calculator in accordance to this formula here, you're going to find already that the function value is 0.00000 out to 5 decimal places. If you plug this value into the f prime equation, which is that one up there, you're going to find that it is 20.19077. And then, once you put that into the Newton method formula, which is this one, you're going to find that your x new value is 4.49341, and then there are some other values of decimal places that I'm not showing here. And when you take those differences between this one and between this one, at that point you'll find that, in fact, the difference between those is 0. So our solution, so our first, let me call this our first 0, or our first, let me just call it the first solution. Our first solution is that x is equal to 4.49341, and as we said earlier, there will be an infinity of solutions in this case. All right, that concludes the discussion for a solution to the transcendental equation tangent of x minus x is equal to 0. I hope that was helpful, and we will see you in a future video.